record it?
Yeah, that'd be great. Oh, it's already filming too. Alright, so we're talking about circuitry today. So I've got some wires here, batteries, and with them we can make a circuit. Little light bulbs too. So, a circuit is just charge flowing through a wire. But what is actually flowing through the wire?
Energy?
Energy, and in what form?
Electrons?
Electrons. So electrons flowing through the wire. So when you have a battery, right, from one side of the battery, electrons leave. They go through the wire because the wire is made of, in this case, usually copper, and it's a good conductor, meaning that it allows charge to flow through. And then the other side of the battery has the opposite charge, the electrons flow in. Now you guys talked a little bit with me last week about how we have conventional current, which is backward from reality, basically. So when I have positive end of the battery, negative end of the battery, what we're really seeing when we write a circuit, right, if I draw a circuit, I have my battery, I have my wire. Now, which end of the battery is positive?
The big side.
The big side. I have a positive, and a negative. So, we know that electrons in reality, right? So reality color is going to be black. Reality, they flow from the negative around the circuit to the positive, right? But conventional current is drawn backward. It's drawn saying that the circuit operates from the positive to the negative, which is just how things are drawn, even though it's not true at all. So when you draw a circuit, that's kind of how it works. So when you draw a circuit diagram, you need to use conventional current, unless he asks you to show where electrons are really going. When I talk about them, I tend to like to just not use conventional current and say...
Why do they keep it?
It's redoing all the diagrams for every building that's over the age.
Oh,
It would be a big undertaking, and then people would be confused, like, is this diagram drawn the old way, or the right way, or what? So people just keep doing it the wrong way, because that's how it's always done.
Doesn't make
Awkward.
scientists look very good.
No, but you know, it's amazing that like Ben Franklin was able to produce a working circuit before they understood the science behind it. So, you know, functionality was good. People wanted electricity. And sometimes we just have to kind of move forward with what we've got. So
Wasn't
we've
one
got...
of the presidents, like, scared of using the lights in the White House when they first installed them?
I think a lot of
They didn't
people
want to be
were.
shocked.
And I think a lot of people were afraid of fire, and that may have been a legitimate concern in the beginning. And at least when you get to physics, we'll talk about how we use circuit breakers, and you know, now we don't have that concern, because if the current increases to the point of danger, our circuits just open themselves up with circuit breakers, or what are the new things? Can't think of the word. So we don't have to worry about heating up to the point of fire in our houses, because...
Fire alarms? Is that what you're talking about?
No, like, if you overheat or overuse a circuit to the point where it gets so hot that it's going to start a fire, it'll pop a breaker, a fuse. Old things were fuses, now we use circuit breakers. They're actually, it's like a piece of one metal and a piece of the other metal, and they heat up at different rates. So when they get too hot, they literally bend, because one metal heats up more and expands more than the other and bends it, and it breaks the circuit open, which is kind of where I'm going next. An open circuit. So what happens if I have this wire and suddenly I have a connection that's just broken? Do you know what happens? Current doesn't flow. This is an open circuit as long as the wires aren't fully connected all the way around, and current doesn't flow. If I put it back, it's fine. And I have a little switch here so we can build a circuit that then we can easily open and disconnect with no current flowing, and close, and then it will work. So closed circuits have current that can flow. There's a path that's made of a conductor all the way from one end of the battery to the other, and current can flow in a closed circuit. When the circuit is open, if there's a break in the wire or an open switch, then current can't flow and the circuit doesn't work. Let's see. The two big things we really need to talk about with current are voltage and current. So the power of our circuit is controlled by the voltage and the current. Only if both are low is your circuit safe. So what is voltage?
How much like power that electrons go through the wire?
Kind of. Power is actually a whole different thing, Max.
How hard like the battery pushes the electrons through the wire?
Okay, so kind of a push.
On
Do we like that?
power?
Yeah, it pushes up the
Power is
electrons.
literally a different thing in circuitry. Like, so it is a good way to kind of think of it, but power is actually like a whole thing. So
It's the push, basically.
that's what he gives you, so we'll go with that. How hard electrons are pushed through the circuit. Okay, and your batteries, when you buy a battery, is kind of rated on voltage. These are 1.5 volt batteries. When I tie two of them together, the voltage essentially just adds up. So I have 3 volts coming from 2 batteries tied together. And that powers the circuit pretty well for tiny light bulbs. Not super awesome otherwise. When you take physics, we'll measure current and see how they work together in a very simple, happy equation. So current.
Like how many electrons go through a certain spot every second?
So it's kind of like velocity of a circuit. So electrons per second, or electrons per unit of time, or how much charge goes past a spot per time. So current, charge per time, is very much like speed. If either one is high, you have a dangerous circuit. In our case, we have both very low. We can touch everything. Even if I had bare wires, we wouldn't hurt ourselves with anything we do in here. Let's look at 2 kinds of circuits, and hopefully I can wheel this thing around so everybody can actually see them. So, does anyone know what the 2 kinds of circuits that the book at least taught you about are?
With the parallel and
Parallel and
series.
series. So, when you have a circuit that's in series, which is kind of how circuits were always done.
Have any sort of ragged ball here.
Hate using this thing. I feel bad. It's not a good idea. Okay. Gently. Releasing gently. Alright. So, when you have 2 resistors, in our case, resistors are like these little light bulbs. You can make resistors out of anything. Like your toaster has resistors that produce heat. I could put like literal resistors in here to control the flow of current. And in electronics, of course, that's very important because you need a certain amount of current going through each type of thing, like in your phone or in your computer. When you have 2 resistors, so here's my battery, and in our circuit, of course, we have 2 batteries, so they line up, positive end with negative end, like that. And I have 2 little light bulbs. Bad drawing of light bulb, right? And if they line up in the circuit like this,
They look like notes.
so if they line up in the circuit like that, right, then conventional current-wise is going to have coming out of the positive end, and the current's going to flow that way, right? And the current is going to flow through this light bulb, and then that light bulb, and then back around to the battery, right? This is in series. Normally you just draw resistors like that, like a little squiggle in the circuit, but I'll draw light bulbs here so you know I'm using those. So this is in series, one light bulb and then the other. Now, when the electrons are flowing through this circuit, do they have to pass through both light bulbs? Every single electron, yes. So every single electron has to pass through that light bulb and then that one, right? So, I built this circuit, and you can see just what's in the drawing is actually right here. Right, I've got one light bulb and then the other one in just a perfectly straight line. I don't know why I've got this clip attached over here though. So, totally stuck. Okay, so you touch here, spatial skills. Now, I attach that there, I need a clip on this end, attach there. And our light bulbs light up. This is no surprise, right? So you can see this circuit, right? So conventional current-wise, we go from the positive end of the battery, up through this wire, through this light bulb, through that wire, through that light bulb, and down, right? So what would happen if this light bulb burned out?
I don't go out to.
And you can see that's true. And in fact, if I just unscrew one, when you have a series circuit, if I just unscrew that one like it burned out, both of them go out.
Kind of like Christmas lights.
Kind of like Christmas lights, old evil Christmas lights.
The new ones don't do that because they're parallel.
Yes. So a series circuit, if one little piece breaks, whether it's the filament in the light bulb and it's completely broken, or you just have a bad connection and your wire goes like that, every bulb stops if one bulb stops. Right? Because they're in series. Every electron has to pass through
All or not at all.
every light bulb. Right. The other kind of circuit is a parallel circuit. And in this case, I'll hook to this battery here. And then my spatial skills. I must need another clip.
Do I have another clip? Yes, I do.
Oh. Okay. So in this case, we provide options for our light bulbs. So I've got this. And I'm not going to plug it in yet, I'll draw it first. I've got in blue, so this is a parallel circuit. I've got my same two batteries like this, and then I'll have this light bulb here, right? And my circuit just goes around, just like I have one circuit with one light bulb on it. But then, and I've got this going on here, right? So, does every single electron have to pass through this light bulb and this light bulb?
No.
No. Some electrons will go like this, and they'll pass through that one and keep going and around. But some electrons will leave the battery and never go through that first light bulb. They'll only go through the second one and around. So when you have a parallel circuit, just like this, if I can hold it up, it's like having, are we lit up? Okay, I broke it. Oh, I broke it so that nothing works. Great, hold on. So I don't want to end up in series. So here, parallel circuit will do this. You have one light bulb that's just hooked up. And then you provide a pathway for the electrons to get through the other bulb without having to go through the first bulb. So, I'll put these inside here. This is so awkward. I'll try to bring it around to each person. See how much brighter one light bulb is in a circuit than two, though?
Yeah, it's
Okay,
so much brighter.
so that's something we need to talk about also. And then I'm going to add this one so that electrons don't have to pass through both light bulbs. So,
They're
you
both
can
brighter.
see, right, the electrons could just go through this one and back, or they could go through this one and back, but they don't have to go through both. So, what do you notice about the series bulbs?
Those
The
are a lot
parachute.
brighter.
So the series bulbs are much brighter. Why do you think that is?
Wait, you mean
You mean the parallel?
The parallel bulbs are
Second.
much brighter, of course. That is totally what I meant. Parallel bulbs are much brighter. Why?
Ah,
Oh, and look, when I
because
break
they're not
that
sharing.
circuit. Right. So what happens when I break? Do they both go out?
No.
No. What if I undo that one? Now they do because there's not a full circuit, right? The battery's unhooked. What if I undo this bulb? So I can take out the first bulb, but the second one keeps working. Because in parallel, the circuit doesn't rely on each bulb having every electron pass through it. There's another pathway. Will this bulb, when I unscrew the first one, does this one get dimmer or brighter? What do you think?
Brighter.
I think they'll stay the same.
I mean, it does stay the same. How about if I take off the second bulb, so there's only one bulb in the circuit, dimmer or brighter?
Brighter.
Can you tell a difference?
Really can't tell.
Can't really tell.
It's a little
See,
brighter.
when I hook it back up, maybe you'll notice. It actually shouldn't be brighter at all. It should actually get dimmer when it loses its friend. Crazy, but true. So yeah, you can't really see the difference. But you can definitely see the difference in two bulbs in a circuit in series versus two bulbs in a circuit in parallel. So Lily just told us a couple of interesting things. So we've got a parallel circuit here. Alright, electrons have more than one possible path in a parallel circuit. And you guys noticed that these are brighter with two bulbs than the series circuit. I'll unhook it for a minute just so we don't wear out the batteries. But when there are options for the electrons to travel, it makes the lights brighter. What do you think? So think of the definition of current, which I erased.
There is hold on. There is
And the definition
there are more
of-
electrons passing through because there's more than one way, I guess.
Okay, so more than one way.
Like cars
So-
on a highway, there's two paths, therefore the cars can get through faster.
Exactly the same, like a one-lane highway versus a two-lane highway, right? Some electrons have more energy than other electrons. That's just how the world is, right? Some of you have more energy today than others. Maybe next week it'll be different because electrons can gain and lose energy. Joshua?
So do parallel circuits use more energy than series?
I never asked me that.
Wouldn't you think they would because they're brighter?
You'd think they would.
Because they're brighter.
Well, because they're
No, because
brighter
the electrons
and-
are also
And
moving.
since
Because
it's a
more
faster
electrons can leave the battery faster, so yeah, you'd think so.
If they are moving faster, wouldn't they have more energy?
Well, they're able to move as fast as they can without just getting stuck behind a slow guy. Because when they're passing through a wire and they have to kind of stay in line, there's kind of a limit to, just like cars on a one-lane road, there's kind of a limit. There's not really a passing lane in a lot of wire. But in parallel, they can zoom out around and choose a path that will allow them to go faster. So, you're gonna have brighter bulbs in parallel circuit. Here, let me. You can hit pause if you want. I'm just gonna make sure everybody can actually like see the two circuits. Now it just loops right around and pass it along. Oh, I didn't put a switch in either. So then we've got parallel circuit. And basically what you've got there is just one bulb in a loop. You have a nice closed circuit. And then you just click in a second.
connected to so many different
Yes,
things.
the electrons
We
flow
got
fast.
one so we could use the whole thing. Except he was missing like one or two pieces.
Pay for that.
So
Pay with that for Meredith and
I
Josie.
didn't have another snaps of a set, but he was junior.
No, I mean, I actually clipped
now Reagan and I each have a set.
it wouldn't even make a
Really big
difference.
things. Just rip 2 snaps of
You can get like snap circuit
What about
No, I wasn't worried about making the name
RCs
for it.
and
I
stuff.
was
It's
just
crazy.
Yeah, the clip was putting
You ever put a big light bulb on?
There's so many different you can there's like pros.
Yeah, this breaks this pathway, but it doesn't break that pathway. So in this case, this bulb will stay lit up, but that one won't. Because you've only opened this piece of the circuit, but not that piece. Now if I put the switch anywhere in here, I called those light bulbs resistors, right? So they resist the flow of current. Even though they conduct electrons, they're still resisting the flow of current more than the rest of the wire. So resistors produce something. So think back to air resistance, think back to friction. When something is resisted, like motion, where does the energy that is doing the resisting go? Right? Like, what slows down the paper?
Air resistance?
And air resistance causes what? Where does the energy that should have gone to falling go? If there were no air molecules to shove out of the way, this would fall faster. So where does the energy go?
He's handed up.
With friction, oh Max, go.
It turns into heat.
Heat. So those resistors produce heat. Resistance in an electrical circuit produces heat. And that's a key point, I think. It impedes the flow of electrons, it produces heat. So if I have, scan your circuit again, sorry. If I have this big, thick copper wire, right, and I've got a little thin copper wire like would be encased in here, which one is going to resist the flow of electrons more?
The small one.
Why?
Because the bigger ones will spread out. For the smaller one, they don't have to go as far. And
Right,
they'll-
just like the
it's just like,
two-lane road. No passing
It's a
lanes,
collide.
more resistance.
It's just two.
So a big, thick wire is going to have less resistance than a thin wire.
it's longer, will have more resistance, but
Yes, the longer, so that's why I hate to add more and more and more clips to my circuit, because I increase and increase the resistance, dimming out the light bulbs until you can barely see them. And then I stick like a nail and half of a pen apparatus, and you know I keep but I keep increasing the resistance of the circuit with everything I add to it, including the wires. And in physics, I'll teach you to account for the wires in the circuit when you calculate the resistance of the circuit and everything. It's really fun, hopefully. So, if you have a fat, short wire, you're going to have less resistance than the long one, which is why I went with this fat wire here instead of connecting the batteries with an alligator clip, because they have thin, long wires in them. And it makes it work much better. So then, magnets. So I've got an assortment of magnets, and hopefully we'll have some time to play at the end after we do the quest and stuff. But, magnets. I need my table to be flatter for magnets. But, alright, so,
Did I do my It's only 12.2, right?
Of the table to maybe make it flat.
oh. It doesn't always stay super flat, but maybe. It kind of wobbles. Alright, so magnets. Magnets always have two ends, and we call them a north pole and a south pole. So when you're looking at two magnets, and these two are pretty much the same magnets, right? You have an attractive force between unlike ends, right? The north pole of one magnet will attract the south pole of the other magnet. And you have a repulsive force between like ends. So just like, and of course you know that the electromagnetic force is one force, so just like charged particles, like repels like, electrons are repelled by negative charges, electrons are attracted to positive charges, north ends of magnets repel each other, and south ends attract to north ends. So opposites attract, and like ends repel. And if I could line them up right, So,
I like pieces of chocolate.
Yummy.
yeah, no, very bad.
Wait, they
pieces
are?
of chocolate.
No.
That would be very bad. So,
Chocolates?
no, not chocolate. Y'all just ate. So, this is magnetic putty, which is fun, and I'll pass around. You guys can play with lollipops.
Magnetic putty.
Magnetic
so cool.
putty.
I need one of those.
So I'm going to show you what the field lines look like
Get
for a
those
magnet.
to class for Christmas.
I want the silver.
Christmas is over.
Yeah, I know.
Someone's
right?
coming.
Easter basket.
I want some.
Tell your parents you want magnetic putty in your Easter basket.
Where do you even get it?
I got this at Michael's, but you can get like big amounts of it online for lots of money. I had a 40% off
Wait,
coupon for
how
this.
would a putty have a north and a south pole? If it's just always,
Okay,
I guess,
so-
discombobulated.
This is a magnet. So Jesse, look, see how the surface of the magnetic putty is pretty smooth? You don't see any little pokey things sticking up really. So if you put it onto the magnet, number one, it'll mold itself around the magnet because it's attracted. But look at the tiny
That's
little
really cool.
bumps that form.
That's so cool.
Do you see those tiny little bumps growing up out of the putty?
Okay, don't
So if
like
you
it.
smooth out the surface, then you start seeing these tiny bumps. Well, what are those? Those are the magnetic field lines.
Yo, wow, you're gonna see magnetic field lines?
Yes, and I'll even do it where you can see it better. And I'm going to do it right here in front of the camera, but you'll be able to see it just fine. So I'm going to take one bar magnet. Hopefully there's nothing super magnetic on the other side of this music stand. And so Joseph and Meredith can see. So I'm going to sprinkle iron filings on this piece of paper, and under the paper is a bar magnet with a north end and a south end, of course.
What is that?
These are iron filings, so they're magnetic. And so they'll be attracted to the magnetic force.
Are those things you use when you buy them at the store and you can like make people have hair?
Yes.
Yeah.
So iron
What the heck?
filings.
Is there a magnet under that?
There's a magnet under there.
And they're attracted to it. It's like exactly like
Not
the
a
things
magnet.
you
I noticed it doesn't attract to the center, it just attracts on the
But do you see the field lines? Field lines going from north to south. You can see the curved field lines.
Can't you like
can
go
see
to
them
the
going.
beach with a strong magnet and get those? Like just gather them up?
If you had a really strong magnet, you could probably pick up a lot of stuff. And I know that's how they clean shops where they have a lot of nails down and stuff. They just take a big magnet and
Very
sweep it across
weird.
and pick up all the magnets.
very
Because one time we went to this beach
No,
that
just
had
wait.
like a bunch of like those iron
I couldn't do it to you.
bits of
Yeah.
rocks
There's
all
more
over, and we
magnetic
gathered like a whole
putty.
bottle of them, and we have those at home.
Miss Mathias, can you put it over here?
If I move it, I'm kind of afraid, but I might just, well, if I open this, it always makes a mess. So I know better. I'm just going to open it on top of the magnet this time. I'll do it over here again.
I'll pick up everything.
Your aunt vacuumed. I feel bad. Don't pick them up with the neodymium. You'll never get the iron filings off the neodymium. It's awful. Ask me how I know.
A neodymium? What?
If you use that super ridiculous strong magnet that Duchesne brought,
Oh, that's a magnet? I thought
it
was a
will
piece
pick
of
up
pencil.
these
I thought it
iron
was a battery.
filings
I thought it
really
was a battery, too.
effectively. But then,
I thought it was like a piece of your pencil. You know, like like pencils. They have that yellow part at the top.
yeah.
The eraser.
can't hold it. Iron dust off.
Can't.
Okay, so,
Oh, then you should put it on it.
I have it on it.
Broke my shoulder.
so if you guys want to see, there's the bar magnet under here.
Let me see that.
Actually, I'm going to draw on the board.
Do you have another bottle?
Is it a really, really
Do you have
strong
another
magnet?
bottle?
Yes.
Give it.
If you put it like through
No,
your
if
Don't
you
ask
put
me, don't
it in like
Yes.
yes.
I can put it through my
container,
hand.
and
Yes.
if you move the
Brian.
magnet around.
Like I can move it. I
it'll
can't
fall
keep it there, but I can move it.
But those are so strong that they will pull
Can you
away
put
from
two
them.
and
No,
two
then you
like
could
that?
use those if you had it in a different container.
I
Like one of those containers, like a
Not through my hand.
beaker or something.
That's true. You could like wrap those in a plastic bag and return the bag. Alright, so what did I want to say? I had something important to say before I did this.
Oh, okay.
What was
Josh,
that
would you
thing?
like this?
Field lines. Okay, so magnetic field lines
Someone
always
got a little
go
hungry
from
during
north to
class.
south. So in a magnet, you have field lines that go like this, right? They always go from north to south. So what you're seeing is literally this field. So if you didn't see the first time, come over and watch this. Look at the magnet first. But can you see the field lines? Field lines flow from the north end of the magnet into the south end of the magnet. Actually, I'll do it differently for this one. Not over the bottom of iron pipe.
South and north.
Do we see my second magnet? Where did I put it? I wanted to get it away.
It's right here.
So. Oh, good. That's it.
I think.
Okay, so then I'm going to put the two north ends as close as they can stand to be from each other. So now there's two magnets under there, right? So I've got two north ends of two magnets under there, and you watch the field lines form just like the picture on the board. You can literally see the field lines.
Look at that.
I see it now.
Isn't that cool? Look for the S in the end.
Yeah, I see it right there.
Did you see the S in the end?
It's right there, the end right there.
So I've got two north ends, and you can see how much they repel each other. Nothing will stick in between there, right? And then you've got the field lines going from north to south, from north to south. So you can just see the field lines. Thanks, you guys, for filming there. So two magnets.
I have to do it.
Form, right, the field lines. Here's a north end, here's a north end. They repel in the middle, and then you can see north to south, north to south field lines.
It's cool.
Can
Can I have some shavings on this?
What do you think they'll do? They'll just stick where you can get everything to spill and see what happens. All right. So
We want it.
Wouldn't it be
Know it. But nobody needs to get on it, Cody. Is there anything special?
Wow.
my phone is boring. So the module 12 quests, we're gonna start.
Okay. Should we give you all your magnets?
I did not get a quest.
Yes, you did. You did too.
Just for being very rude.
I can't do it.
I'm not rude to you.
You have to touch. You have to touch. There we go.
Hey,
Let me see.
Keep hitting my head.
Got the knee. Let me see. You touch it to my braces. That's weird. You're like.
Huh? Just
Which
touch
is
it. Yeah,
just like the force for gravity with the mass of one object times the mass of the other object, the change in the amount divided by the change in the distance squared. The magnetic force is the charge in the first object times the charge in the second object divided by the distance between them squared. So Max,
Ms. Mathias, would you like me to do the problems right now, or just...
up to you. You don't have to write the answers down. You can just watch, or you can go hide, or you can write it down. Whatever works.
She's gonna go high.
If you don't want to see the answers, ignore and watch the video later. So, Jesse, the only thing here that changes, the charges on the magnets, the amount of magnetism doesn't change, but the distance between them is quadruple. So what is a factor by which the distance change if it's quadruple? Well, the charge is
12. It's 1/4. 1/4.
Okay, so when the distance is quadrupled, it's multiplied by 4, right?
Yeah.
And
So
then you
is the answer
square it.
16?
Well, let's find out. So what's 4 squared? 4
16.
So what happens to the magnetic force?
It is.
Just
It increased.
it increased. Did it? If it's in the denominator?
No, it's decreased.
Okay, so the magnetic force decreases by 16 times. So if you end up with an answer in the denominator, that force is decreasing by 16.
Miss Mathias. Is this for number 1?
This is number 1 on the quest. So Patrick. Oh wait, there's a
But is
second
it
part.
force is attractive or
Patrick.
is it repulsive?
So if you have Patrick or Jesse, let's stick with you since it's your problem. It says the force between two south poles. So if I have two south poles facing each other, are they going to repel or attract?
Repel.
Yes, because the like ones repel. So I got two south poles, they repel. So is this force repulsive or attractive? Because it's two south poles.
Also,
I didn't see that part of the problem. I didn't
Two
know.
south poles. So they're going to repel each
I
other.
was so confused.
So they're repelling each other less
Yeah.
because they got further away. Okay? So number 2, Patrick. The force between two foils is measured. So think the electroscope and the foils. If the charge on each foil is tripled, okay? So charge on each foil is tripled. The factor of change will be 3, right? And the distance between them is doubled. So the factor of change for distance is 2, right? So what will the new force be like compared to the old one? So how should I plug that in? What should I do?
So it's 3 times 3 over.
connect.
So can I
Just
plug that in there?
disconnected.
What should I write? So in the numerator, the charges, right?
It'd be 24.
Okay, he did the math all in his head, so I'll do it out for those of us who can't go that fast. So the charges both increased by 3 times, so I put a 3 in for that charge and a 3 in for that charge. And the factor of change for the distance was 2 times, right? So, right, you have to square the distance in the denominator, okay? So then I get 9 in the numerator, and I get 4 in the denominator, right? So, what can I say about how much the force changes? Brett?
I just knew it's getting larger.
It is getting larger, because 9/4 is, well, if we made it look like a number that we all understand what would be. Think if I made this a mixed numeral, Chris?
Is it 2 and 1/4?
Yes. So 9/4 is really 2 and 1/4. If you just take that fraction and make it into a mixed numeral, right, it's the same thing. It equals 2 and 1/4. So you could say the force increased by 2 1/4 times. Just a little more than 2 times bigger. Okay?
So when it says by what factor is each charge increased by 2?
My paper says 3. Did I change it?
Oh, then 3.
Yeah, so the charge increased by 3 times, and the force increased by 2 times. So the total force, because increasing the charge makes the force get bigger, but increasing the distance makes the force get smaller, because it's in the denominator. So the total force is going to increase by 2 1/4 times, or 9/4. It gets bigger by 9/4 with the sign. So extra fractions. I don't think you'll get fractions like that on the test. You'll probably get a whole number on the test, not a fraction. Oh, let's start over here. So Jenna, number 3 says, if I charge an electroscope with a positively charged metal rod, so kind of the opposite, we use a negatively charged balloon. If I get a positively charged metal rod, and that electroscope gets a negative charge, did I use induction or conduction?
Yeah, we charged it by induction.
Induction, how did you know?
Because when you charge it by induction, you get the opposite charge.
Exactly. Induction gives you the opposite charge that you had on the thing you were using. So 3 is induction. And 4, Elise, my Christmas tree lights are in series. If one bulb burns out, will the rest of the bulbs keep working? No. Series circuit, if one piece burns out or breaks, the whole thing is done. Not any electricity can flow from one end of the battery to the other. And Stephanie, if I use a negatively charged balloon to charge an electroscope by conduction, what charge will the electroscope get? Negative. Negative, because conduction gives the same charge as the thing you're using to charge it. Okay, so we did the quest, yay. Let's keep going that direction on the, what are we doing? Study guide?
Okay, so where are you pointing?
What? I was on the question,
Yes.
asking a question.
Erase the one.
I didn't really, this week, I thought the magnets were kind of confusing. I was these.
I have some little neodymium guys, but I don't know where they are.
I think we stopped on question 12.
Yeah, it was
Oh, right, we did some of this last week.
question 13.
Okay, so we're gonna start on 13, and I have no idea where am I gonna start about.
Is that strong?
And we already basically practically answered number 13 while we were doing.
I'm sure we've answered nearly all of it, I
But
hope.
we still have to go through. I think we
Yeah.
stopped at 12. So I think we're on 12.
Well, Lily, you do 12.
Okay. The
What is
question,
wrong with conventional current?
assuming that electricity is the flow of positive charges.
Right, exactly. So they assumed electricity is the flow of positive charges, but it really is the flow of electrons, which is the flow of negative charges. So you always draw your circuit essentially backward from reality. Passive and magnets, they're all dying to play. Number 13 is for Ava. You have 13. You have 2 wires. One is long and the other is short. Which one has more resistance? The long wire has more resistance. If you're just comparing a long wire to a short wire, a long wire has more resistance. Chris, you have 2 wires. One is thin and one is thick. Which one will get hotter if the same current is run through them?
The thin wire will get hotter
Thin wires get hotter. Why?
because there's more, I guess, congestion.
Can't
'Cause
spread out as
They
much.
can't spread out.
Yep. So the 1-lane road is going to have more resistance than the 2-lane road. Let's see. So Ryan, and so in number 15, you have to look at the picture. One has a circuit with an open switch in a parallel, that's B, and then an open switch in a series circuit, that's A. So in which circuit can the bulb work? B can work. Why? Is there a complete path for the electrons to flow?
Yes.
Yes. So if you have a closed circuit, a complete path from one end of the battery to the other, electrons can flow. In B, that's the case. In A, it's not the case because there's an opening that just breaks one half of the battery from the other. 16 for Duchesne. 3 lights are in a room. When one burns out, they all go out. When you replace the burnout one with a good one, the other 2 lights work again. Are they in parallel or series? Series. And it should really say all 3 lights work again because it sounds kind of like the new one didn't work.
You're right.
They all 3 work at the end. That would be a fancier circuit than I can deal with, indeed. Joshua, if it takes a flow of charged particles to make a magnet, where is the charged particle flow in a magnet?
Wait. They're all in the same direction. All of
What are they?
the electrons are pointing to the same.
So every atom has electrons orbiting. And if you align them so all their electrons are orbiting in the same direction, then you've got a flow. And that makes a magnet. Some materials just can't be lined up. Like we could bang on this table forever and we'd never get the atoms to line up so their electrons go in the same direction and we can get a magnet out of that table. It's just not going to happen. It's plastic. Oh my. Where are we? 18 is for Max. Is it possible to have a permanent magnet with just a north pole?
No, ma'am.
No, you need a south pole too. Never have a monopole.
That's been recorded.
Wait, what happens
Not
when
yet.
it's just a monopole?
It-
What
it doesn't
happens?
I don't know. It never happened.
It'd be weird. It's like, I guess it would be repelled from itself, and then it would break into 2.
But those 2 would be monopoles? I don't think. I don't think it's possible. But we'll see. Someday maybe. Or not, because it's probably not possible. Patrick, is it possible to make a magnet from something that is not a magnet?
Yes.
Yes, you guys did that with the electromagnet. You just some materials can have their electrons lined up, but they're not naturally. And Jesse, if a material does not respond to a magnet, what can you conclude about it?
It's not, atoms cannot be aligned.
Or at least are not currently aligned. Because some things you can eventually line up if you expose it to a magnet enough. Like if I store my magnets in the same container with my compasses for a year, guess what happens? All right, thank you.